Welcome everyone, and today our discussion will be on the forecasting application. In this notebook, I'm going to follow a book called Chapter 7 of this book, Forecasting Principle and Practice. And we're going to follow some of the example they have in the Chapter 7. This is the book, and this is the exponential smoothing technique. But before that, we're going to also talk about some of the so-called moving average method. So in this lecture, we will cover simple moving average, cumulative moving average, exponential moving average, and also we'll cover three different type of exponential smoothing, simple exponential smoothing, host method, usually referred as exponential smoothing with a trend. And we're going to introduce the standard and the damped version. Lastly, we're going to introduce the exponential smoothing with a trend and a seasonality. And this is usually referred as a Hose and Winters method. In this notebook, we will introduce additive and multiplicative version of those to see. Okay. First, let's load some simple data set to illustrate our algorithm. And later part of the notebook, we will introduce some of the more real world data set and to make sure that it works. And first, we're going to introduce to import panda, import matplotlib, pyplot, and numpy. These are the almost standard import right now. I'm going to also load the data set. So these are already typed it up for you, so you don't really need to type again. Okay. So for example, the oil data we have, we can see that this is our data looks like from 1996 to 2006. And this is just a small data set for you to, for us to explore. All right. And then first we're going to introduce the moving average example. So this is a test data set, manufactured data set, and called product, including the month and the demand. Okay. So I'm going to run that. All right. So this is a very simple data set, months 1 to 3 to 12, and demand and given. So total number of rows is 12 in this case. All right. So to calculate, for example, moving average from 0 to 10, since we have 12, so we're going to do very simple ones. We're going to do df dot location. I'm going to add, sorry, index I plus 2, so we will have from 2 to 12 instead of 0, because moving average, the first couple are 0. Then we're going to call this simple moving average, okay? Of 3 period, for example, and equals to, let's do this first. What we're going to do is we're going to have df using iLocation. We did this in our in-class quiz, so I'm sure you already know what I mean. We're going to do, from I to from I to I plus 1, I plus 2. So here we have the okay, these three added together, then divided by 3. Okay, so originally it's like that. So I'm going to run it only to the first one digit under the decimal. So here I'm using MP run, for example, and get it to leave only one significant digit. So here is we're adding, okay, loop through everything and adding that. So this is what we want to run, and also then I'm going to have I is in range of from 0 to df shape of 0, for example, minus 2, meaning df the shape. What you have right here is from 0 to the shape. The shape of the 0 is actually equal to 12 minus 2 equals to 10. So from 0 to 10, I'm going to add the I plus 1, I plus 2 together. And then, sorry, and divide it by 3. Okay. And take a look. So now you see that the first two elements are no value because the first value moving average is average of the first three number and so on. And the second average will be the second to the fourth number and so on and so forth. So this is the moving average 3. Okay. So here I'm going to print it out. All right. Keep getting the results not defined. Oh, this is easy. And we just have to initialize the result first. Okay. Result equals to the Panda data frame given by all your data. Okay, and also I'm going to resolve, for example, I'm going to rename the column. From 0 to, for example, demand. Okay. And here I'm going to equals to true. Okay. And then also I'm going to create a new column called simple moving average 3, period. And they all equal to 0. Okay, I'm going to first I'm going to create a result data frame and rename it to demand and simple moving average 3. Then I'm going to run this. You can see, and you're going to see that this is moving average by hand totally. Next, we're going to using the rolling function. The rolling function is fairly simple. I'm going to create both version results. I'm going to create a column called using Panda directly. Okay, SMA3, for example. This column equals to the results directly. And my location for all the rows, column 0. I'm going to perform column 0 is the demand, basically. Okay, and I'm going to do the rolling. Here, the window equals to 3. And then take average. Okay, so here I'm going to see the result. Okay, so you see that now is the pandas rolling for window for 3. I can make a duplication again for that. Add another column. Oh, sorry. Okay, instead of using rolling function, so now I'm going to make a copy. Instead of call it 3, I'm going to call it 4, and windows equals to 4, for example. And I'm going to execute it. So now you see that we have pandas moving average 3 and panda moving average 4. Okay, so included right here. And next we're going to do is doing expanding function to calculate so-called cumulative moving average. The cumulative moving average is the same thing. I'm going to have fairly simple. I'm going to call it cumulative moving average of 4, for example, and equals to result, location. Okay. For all the rows and 0 column, which is the demand. Then I'm going to do the expanding function. Okay, minimum period equals to 4, and I'm going to take average in that sense. Okay, and you will see this, the last column added right here, so the cumulative moving average. what it does, the cumulative moving average is taking the first 4 number and take average. So these two are exactly the same. Okay, the fifth one actually is the average of first 5. Okay, so you see there's a slightly difference between the panda simple moving average 4 and the cumulative moving average 4. Okay, and then you take the first 6 and then take an average. So you see that this number becomes far and far away from the simple moving average. So there's no rolling window. Is keep every time it's starting from the first position to up to whatever current it is. Okay. Next, I'm going to plot these things. Okay. So I'm going to quickly do this. There's quite a bit of type in. I'm going to have PLT dot figure figure size equals to, for example, like that, 8, and PLT grid. Going to turn it on so you'll see the grids together and resolve first. Sorry. I'm going to plot first the demand portion. Okay, resolve, for example. I'm going to use mark equals to O, which is then I'm going to give a label. Let's do data itself. Okay, and then I'm going to particularly call the line width equal to 3. In this case, I'm going to do the plotting the second one. Okay, resolve. Three. Let me see, SMA 3. Here's the underscore right here. And I'm going to call label equals to, for example, SMA 3 month. Make a copy of this. Getting SMA 4 month, for example. And then I'm going to make it easy. So here, the last column is cumulative moving average. Here, moving average of 4. CMA 4 month. Okay, and also adding a title. Very simple. Show you the long way to do this. And what we have is compare different moving average method. In this example, okay, And finally, I'm going to plot the legend. Okay, so now you can see that the pandas SM simple moving average. The blue lines, thick blue line is the original data, and SMA3 is the orange line. SMA4 is the green line, and the cumulative moving average is the red line in this case. So this is a fairly straightforward plot. Next, we're going to continue doing the cumulative moving average for the air quality data. I'm going to reading the data for now. What we have is the column we have. We have actually 16 columns, and the 15 and 16 columns are unnamed, so they are not valid data, and we don't need to. So here, what can we do is we're going to drop their last one, 2. So I'm going to drop their last column, 2 column. So I'm going to redefine df. Why do we do this? Drop. This is easy. We do this. We define the df equals to the df for the I location. Okay. And for all the rows, but only for the 0 to 14th column we have. All right, so that's first thing, very easy. We can do that, redefine df. So then we can type in df. Okay, last 2 columns got dropped, but we still have some of the rows actually are no value. So it's empty rows. This is purposely I created this mass in the very end. So I'm going to drop those rows as well. Before that, let's do that, see how that's going to go. So I'm going to see if is NA. I'm going to do a count or summary for that, and you will see we have 114 of those. Okay, and it's NA. So we're going to quickly drop those. So df drop NA, and I force in place to do it. So this is a safeguard. In place equal to true means actually perform the drop of the rows instead. And without the in place equal to true, they will show you the result, but not actually change anything for the data frame. I'm going to do that. Sorry. I'm going to do this again. So you now see all the null rows are deleted in this case. Next, what we're going to do, we're using cumulative moving average to the temperature column. So let's quickly separate the column from the complete data. So what we can do, we're going to create a different data frame equals to panda data frame from the original df. Okay, and just need the last two columns for all the rows, but using the last to the second column, which is this column. Okay, second to the last column. All right, and then we can demonstrate. This is the temperature we have. And then we're going to do accumulated moving average of 4. So create a column called accumulate moving average of 4 period equals to expanding and minimum periods equals to 4, and then take a mean of those. Okay, C for X, expanding. Notice our original data set with the day and the times right here are two separate columns. Now I want to convert it. This is hours to hours data. So I want to convert the day and the time into one single column called daytime. All right, so here what we have, and then compile using a daytime. So here I'm going to create daytime, since I already column equals to df daytime. Okay, and to apply to a function. This is called the lambda function. Lambda function, what we have. The lambda function is, we work on x, is the daytime. The string to time, okay, for example. And all the columns right here equals to, for example, now we have years, a day, month, years, and hours, minutes, and seconds. So how do we do that? So I'm going to have this day, okay, slash month slash year. This capital Y means the 4-digit years, and a space with hours, minutes, and seconds. Okay, I'm going to check the DF for now. Okay, first we combine a day and time columns into a daytime column, and then convert it into daytime information. And you can probably see right here, the last column is the daytime information. Okay, and then finally I'm going to do is I'm going to set the daytime information as the index. Okay, so this is what we're going to do. So df of t equals to its index equals to df dot daytime. For example, I'm going to see df of t, how it looks like. Okay, so df of t looks like this. Okay, so the temperature data and the cumulative moving average, the index is the daytime. Okay, finally, we're going to plot it. Okay, so here you see that we plot this, and the orange data is the cumulative moving average, but you see there is legends is on the location 2, as on the upper left corner. May not be so visible. Let's change to 3, see what happened, and you'll see the legend match to the lower left corner in that regard. Okay, so we're plotting the original data in blue, and the orange data actually is the cumulative moving average. Next, what we do is we're going to do the exponential moving average in the sense. We're going to import the stats model tsa.api. I'm going to see how that's going to go, and then I'm going to perform a so-called exponential moving average, and this is fairly straightforward. So exponential moving average, add the columns in that data frame. Sorry, I'm going to using for the temperature. All right, and then I'm going to have high location for all the rows, but the first column, which is the T column, or temperature column, I'm going to do the exponential weighted moving average, usually referred as the span actually equals to 40, okay, total 40, and adjusted equal to false. All right, and take a mean of that. All right, so here we go. And then we see df of t, and you can see that what happened. We create another additional column called exponential moving average. Now we're going to plot it. Same thing. Location equal to 3, and see that how it goes. So you see this. Actually, the cumulative moving average is orange as before, but the green lines represents the exponential weighted moving average in that sense. And it clearly follows the patterns of the original data, and even with these outlier of zero temperature. And this zero temperature is just missing data. We'll show you how to deal with these missing data later on, but right now, the algorithm itself actually performed very well, surprisingly well for that purpose. Okay. So the next we're going to do is we're going to perform simple moving average. So simple thing. All right, and then I'm going to do 3 different fit for this. Okay, simple exponential smoothing using 3 different fit, different version of the fit. The first one we're going to do alpha equal to 2, the smoothing factor equal to 0.2. And the second one, we're going to choose alpha equal to 0.6. And the fit number 3, basically I asked the software, stats software, stats model software to automatically find the optimized alpha for it. So here I have 1, 2, 3 different fit and 3 different forecasts. So forecasts are only for 3 period. So here we have 3 period. One with the alpha equal to 0.2. So right here, the smoothing level equals to 0.2. Or the changing the smoothing value equals to 0.6. And then if I complete missing the smoothing level, and then the software will automatically, the routine will automatically determine what is the optimal smoothing level. So I'm going to run this, and you'll see that 0.2 alpha equal to 0.6, and alpha equals to the optimal, which is alpha equals to 0.89 something in the green. And that's the optimal one. And these are, this portion of the data is what we call the prediction. And this portion of the data we usually refer as forecast. So the prediction is the prediction on the data you already seen. Okay, we call it in the sample prediction. And this portion is you don't have the actual data and you just do the forecast into the future. So this is what we call the out of sample forecast. So these are the terms I use in the class. So if I say prediction, basically means in sample, which means I trying to produce a prediction based on the data the model has seen. And this portion, without any further data, I'm going to call it out of sample forecast. Okay, so here we trying to make the naming consistent a little bit, so you know what I'm referring to. Okay, and the second method we're going to do is the host method. The host method basically, I'm going to copy this portion over. So you can see that. So host models actually is exponential smoothing with a trend, and this method is proposed in 1957 by Host, and expand their simple exponential smoothing into handling so-called trend. And this notebook, I'm going to introduce 2 versions. One version is the so-called standard version. The other one is damping version. Okay, so here we have a y hat, which is the predicted value equals to L plus H times B. L is the level, forecast the level. B is the forecasted trend, and these things added together. Okay, so the level is exponential smoothing as well. Okay, you can see that. And the trend is also basically the difference between the level, we call the trend, and times beta, 1 minus beta times the previous trend. And here is a parameter called phi. Phi equals to a so-called damping parameter, how big it is. So here what we have, we're using an H, meaning H step forward damping. So the phi itself is between 0 and 1. When phi equals to 1 means the standard exponential smoothing with a trend without any damping effect. Okay, so these are the clear definition of those terms in the equation. We're also going to propose 3 different types of fits in this section, which is exponential smoothing with a trend. The first one what we do is we're going to do choose not to optimize and provide the explicit value of alpha and beta. Remember, alpha is the smoothing factor for level. Beta is the smoothing factor for trend. Okay. The second fit, fit 2, is exactly the same as a fit 1, but using the smoothing level equals to point A, point B, and about the same thing, and smoothing factor. Okay. I'm just using the exponential part of it for the fit 2. The third one, I'm going to using the damping trend equals to true right here, and using exactly the same smoothing factors and for both level and trend, see what happened. So now you see the data we have for the air quality data, okay, air quality data. You see these are the in the sample prediction from the very beginning. The black ones represents the black one represents the original data, okay, and then the blue one represents the holds a linear trend. Red one represents the exponential trend, for example, and green one represents the additive damping trend. And you can see that. And these are the three forecasts out of a sample forecast into the future without the support of a current data. All right, this is so-called exponential smoothing with a trend. All right. We can also perform the seasonal adjusted data, applied it to livestock data set we had, and we can do the comparison and see what happened. So here we have 2, 3, 4, 5 altogether, plus I'm going to plot one of them. And you can see, this one we get rid of the trend and see what happened. And the second one is what's the trend? It's a downturn trend in that case. And rest of the components are relatively the same. The level is relatively the same. So only the slope actually I eliminated. Next example, what we have is we trying to apply it to more realistic data. This is retail trading data for the so-called return. So here in Australia, this is for 2018 and 2019 data, and this is the link referring to that data set. All right. So this is the data set we're going to read in for the data. And the data set looks like this. From 1994 all the way to November 1919. Okay. 2019, I'm sorry. And this is the data plotted, turnover. And you see that there's clearly seasonal patterns involved. The reason we're going to introduce this, there is two components involved in this data set. First is the trend. And actually the retail data actually trend up quite a bit. And also you see there is a clear seasonal pattern, and the magnitude of the seasonal pattern now also grows. So for these type of data, we clearly have two different phenomena happen in the time series. First one is the uptrend itself. The second one is the seasonality pattern. And the third one is the magnitude of the seasonality patterns actually also grow. See how we can apply our method, learning so far towards the method. So here I'm going to convert the data from here using 3-letter month and the year into a standard year, month, and date. Since we don't have any day information, we just assume that's the first day of the month, okay? Now we're going to run the converting panda daytime index, converted the column day into a daytime information, converted daytime index information, add a column to it, and then going to assigning the index to the Australia retail set. So after that, you can see this is our data frame looks like. The index is the daytime index, and also we have extra day like here. We can drop it. So you can go ahead, drop that column if you want to. I'm just comment this out so I can repeatedly run this demo to you. Okay, I'm going to just choosing the first 100 data since this is a long time history since 1994 all the way to 2019. Okay, and so I'm choosing the last 100 data. Okay, or first 100 data, which is for that. Okay, and I'm going to run the model. And we can actually choose the last 100 data is the same. If you want to choose 100 data, -100 to all the. Okay, so here it is. Okay, and then we can see how that's going to go. So from 2011 to 2019, I'm going to run this model itself, and you can see that. This is what I have so far. Okay, so based on the historical data from 2012 all the way to 2019, and then I'm going to start forecasting afterward. So you see that actually in this method we have, actually I have 4 different models using different combination of the trend, which is additive, or seasonal is additive multiplication. So here what we have is using the triple exponential smoothing with the seasonality. And you can clearly see that in the sample prediction are very close following the original data for the last 100 data point, and also the out of sample forecast also followed the big trend of the seasonality pattern and the trend itself. So it's basically followed that. There's a missing link between here and here, but this is what it looks like, almost like this. Okay, magnitude out. So here is this method is Ho and Winters method, actually. We're going to introduce is the Ho and Winters method, seasonality method, and basically Ho's and Winter both propose this method is to expanding the exponential smoothing with the trend to further handling the seasonality pattern. Okay. So there are 2 different type of models in here. One is the additive model, and the other one is the multiplicative models. The additive models is more straightforward, and for each forecast, you have a level equation, trend equation, and the seasonality equation. Okay, seasonal level equations be updated as an exponential smoothing factor like this again, and the trend component is also exponentially smoothed, and finally the seasonal pattern as well. It is exponentially smooth. So alpha, beta, gammas are the three parameter we use, okay, for the seasonal forecast. Here what I have is the multiplicative model. It's a little bit more complicated. It's equals to the forecast of y equals the level time plus the magnitude of the seasonality of trend information times the seasonality pattern. And these are the equation: update the level, update the trend, and update the seasonality pattern. We're going to use this again to do the Australia pattern. So we can see this is a fairly smooth type of thing. And we get, okay, using the old data, you see that as we had it before, and closely follow the in the sample prediction, okay, and the out of sample forecast. It followed the previous pattern, even without the data. Okay, so, and here is showing for each time period what is the forecast value, the original value, the level parameter, the trend parameters, the seasonality parameter, and finally the forecast. Based on this equation, we have right here either the multiplicative or the additive. We can calculate the forecast column. So I'm just going to summarize that into one tableau for you to see. Okay. And finally, the Holden Winters method with the damp. Okay, the damp is the same thing. The edge portion got changed to the 5, the series of 5 of damping curve. And all right, let's move on to finish this. And what we have is now we are going to run for Dow Jones Industry. And let me see. What is the most current data we have? Okay, we're going to do the Dow Jones information from 2020 all the way to January 1st of 2020 all the way to February 13, last week of information for 2026. And let's look at the data itself and look at the plotting. Okay, this is the Dow Jones. Just keep going up for the significant period, and then we're going to see if we can convert it. Okay, so now we can see that the day got converted into a time data, and then we're going to set this to index. Okay, so you see that Dow Jones Industry, the day is the index, and these are the open, high, low, close, adjust the close, and the volume. Okay, and you can see the information. Actually, we have 1,538 data point, total 6 column, and daytime index. Okay, first column is the daytime information, and rest of them are just floating point. The last volume information is the integer. Okay, so I'm going to choose the last 100 column, and we'll see what happened. Let me see if this is happening. We'll choose the starting day minus 100, which is the, using that as index. So I'm going to have the last 100 information, okay? And then I'm going to count total 100 of them and plotted the information. And this is from, okay, last 100 data set on this daily Dow Jones Index. Here what I have is I'm going to run through this exponential smoothing. I'm going to convert it. Total count was 100. I'm going to be using only 100s too. Okay, and fill that. I'm going to fill the null value to the previous row, and so that if that's the case, we can have no missing data. So now we have 100 still, so this is fine. For stock data, we have weekends and there's no trading, so the data itself is discontinued. For that, I can run the, sorry. Oh, it doesn't matter. Now the data itself is for the data, not even with this clear trending or seasonality patterns. Actually, this forecast is not bad at all. Okay, and I'm showing you two different methods, and one is more aggressive with multiplicative on the trend, the seasonality. So you see the giant magnify of the seasonality patterns in the end, in the forecast portion, and the trend portion follow pretty much the same right here. Okay, so here what I have. Yeah. Okay. Here is the alpha, beta, 5, gamma, initial level, initial trend, and the sum of square arrows we have for each one of the model. Okay, we have. So here, the internals for each day, what is the internal, the true Y value, the level parameters, the trend parameter, the seasonality parameter, and the corresponding forecast. All right. And this pretty much summing up our lecture on this portion. Again, from this notebook, we introduce the following 6 methods. First is the simple moving average. Second is the cumulative moving average. Third is the exponential moving average. And then fourth is the simple exponential smoothing. And number 5 is the exponential smoothing with a trend. We introduced standard method, standard version, and the damped version. Number 6, finally, we do a Hose and Winters method, which is exponential smoothing with a trend plus the seasonality effect. We introduced the additive models and the multiplicative model. And initially, we're using some toy data set to illustrate the algorithm. Then gradually, we introduce some of the real-world data to see how they can be applied to using this method to perform forecasts. I'm going to conclude the lecture today, and we'll continue with the next lecture talking about ARIMA models and using that for forecasting Bitcoin data. All right, we'll see you in the next